Welcome back, students. In this module we are going to learn about, still going to discuss about stacks. Continuing, in the earlier module we have talked about the concept of a stack and how it is implemented as an array. But the same concept of stack with the same operations, now the representation is going to be different, and that different implementation using linked lists is what we are going to discuss and try to learn in this particular module. So that is going to be the learning objective here. At the end of this module we should be able to understand the implementation aspect. Behavior is still the same. As you see here, same operations we are going to talk about, but the implementation aspect, we are not going to use an array, but we are going to use the linked list notion, the notion of a linked list, in order to implement the idea of a stack with the same operations, same notion of it being a last in first out structure, shrinking, growing, with the same set of operations which are push, pop, and finally the checking of whether the stack is empty or not. In order for us to use linked list representation, if you can recall, there is something called as a self-referential structure. When we need to link up a chain of nodes together, we need to have, like I said, self-referential structure. We have already discussed about self-referential structures in an earlier module, but just as a quick recap, what we need to have to begin with is a basic structure. Now assume that I have a very simple structure, the self-referential structure defined like this. The name of the structure I am giving it as node, and there are only two members. One is an integer, the name of which is data. Another one is a pointer, the name of which is next, and the type of pointer is struct node itself. That's what makes this structure a self-referential structure, and you can visualize each node like this having two parts. One is the integer data, the other one is a pointer. So assuming this, now let us assume that a stack is already created for our understanding purposes, and currently the stack represented as a linked list looks like this. I want you to clearly notice the structure. The top here is nothing but a pointer. Top is nothing but, it is also a pointer of, top here has been declared as a pointer to struct node. So currently this pointer is pointing to this node, and this node in turn is pointing to this node, and this node in turn is pointing to this node, and the stack ends here. That is denoted again by the null pointer here. So that is currently the state of the stack. Now how do I carry out the push operation into this existing stack? That's what I would like you to clearly look at. Before we write any code, let us try to physically understand how to push or insert one more node. What does the push operation do to this stack? Obviously, because whenever you push an element into the stack, the new element has to become the first element. That is, first you create a node, assume that I want to insert 40 value, but where am I storing that value 40? Into a node like this. So first you create a node, assume, and into the data field you put the value 40. Now we must arrange the pointers in such a way that now the top must point to the new node, and the pointer field of that will point to the previous top node. So now the 40 element will become the top node, that will point to the previous top, that will point to 20, that will point to 10, so on and so forth. So again to repeat, this is the existing stack. I want to insert a new node which obviously will become the top now. So what do I mean by that? When that is inserted, in effect this arrangement should change like this. Top should point to this, and the next field of this new node should point to this. So that is the effect of the push operation. So what you have to carefully look at is very simple. There are some basic steps here. The first step is, first of all, you have to create the node. You have to put the value 40 into the data value. Then you must assign the address of this node into the pointer field of this new node, and the top pointer, which was earlier pointing to this node, has to be changed so that it points to the newly created node. So to do this, the steps are very simple, but because it involves pointers, it involves dynamic memory allocation. The steps I am going to give you one by one. For the push operation, first step is you have to create the node. The node was not there before. Because you want to push a new element, we need to create this node dynamically. I want you to look at these two lines here. New is a pointer declared as a pointer of type struct node. The next line here will dynamically allocate using the malloc function a new node, as you can see here. The type is over typecast. These many bytes are allocated, cast to this type and assigned to new. The effect of this is simply, we will go back to the original case. The second line here again allocates a new node. For example, because of this line here, a new node is allocated and then it is pointed to. That is the situation because of this code here. What is the next thing we need to do? I want to put the value of 40 into this box here. How do we do it? Simply, this line here puts the value 40 into this box, because this is the data value pointed to by new. So new cap, the member name is data, get the value of 40. What else is remaining? We said that the pointer of the newly created node must point to the previous node which was at the top. How do we handle that? This value should be the address of this node. But where do we have the address of this node right now? In the top pointer variable. So this line here, new cap next, that is this box here, gets what value? Top. What is the value of top? Top holds the address of this new element. So because of this statement here, this link is established. This link is established because of this code. But both top and this are pointing to this node right now. What is remaining to be done? Like we have just discussed, top needs to point to the new element. How do we do that? Very simple. Since the address of this node is held in the variable new, that has to be copied into top. So this line here will simply establish this link. So now it is nice, whatever value you have pushed in has now become the top of the stack. That in turn is pointing to this, and the link is as it is, with only the new node being pushed into the top of the stack. So here the only thing that we have to be careful is the physical aspect. First, if you understand the physical aspect, how are we creating a new node? There is an existing stack already as a linked list. Where this new node has to be inserted? Obviously it is at the top of the stack. In order to do that, what are the structural arrangements of the links that we have to take care? Physically, if you understand that, the code will automatically follow. Now let us try to look at the pop operation. Pop operation is in effect a complete reverse of the push operation. We add one element there in the push operation, we remove the top element in the pop operation. That is, considering the stack as it is, what will the pop operation actually do to this stack? That is, after the pop operation, obviously the code should obtain the value of 40, and after removing the top element, it should get back to the position that we started before the push operation. That is, right now the links are like that. After this element has to be removed because of the pop operation. Once that is removed, again the links have to be adjusted. In what way? Now top should be pointing to the element which comes after 40. That is one thing. And then this node should be freed. The memory occupied by this node has to be freed because it is dynamically allocated. So whatever memory is occupied by this node has to be freed. So that is the effect of the pop operation. That is, one thing is get this value, adjust the links so that top now points to the next element, and then completely deallocate the popped element. So this is the behavior of the pop operation. But those steps, how do we carry them out in C code? I'll just show you that now. Declare a pointer. The effect of this code is this. Q will also point to the top element now. Then now consider these 4 lines of code which will exactly copy the behavior of pop. This line will declare a new pointer which is made to point to the same element. That is the current scenario. Top is pointing to this element, Q is also pointing to that element, and this is the rest of the stack. We need to take out this element 40. What is the next step I am doing? I am getting the value of 40. That is, x is another integer variable to which I am getting Q cap data. This could be top cap data also, both are same. Q cap data, that is 40. 40 is put into x. So I got the value. Then what? I need to make top point to this node. For that I need to have the address of this node. But where do I have the address of this node? That is here, in this small box here. And how do you refer to this small box? It is nothing but either it is top cap next or Q cap next. So that should be made as the new top, so that instead of this, top will point to this. But the address is here. So you can write top is equal to top cap next, or you can simply use top is equal to Q cap next. That is, Q is pointing here. Q cap next is this address, which is nothing but the address of this element. That is what I want to put into top now. So that top will point to this, and this line here, top is equal to Q cap next, will make top point to the next node after the one which is going to be eliminated. So that the stack starts from here now. Top of the stack is 30. Of course, these links are still there. So now what do we do now? We simply free Q. That is, by using this particular statement here, we are going to completely deallocate the particular memory occupied by that node. So first thing is, visualize the stack as a linked list, then know exactly what the pop operation must behave like, understand that. And once you understand that, in order to get that behavior, what are the minor steps that we need to take care so that the stack gets adjusted the way we want it to be. So if you can understand the physical steps, the code will automatically follow the thought process. So this is how the pop operation works when you are using a linked list. Now at the same time, you can consider what happens when you go on popping one element after the other until the stack becomes empty. Go on popping. As you can see here, when you go on popping, once this is popped, there are 3 elements. When this is popped, top will point to here, this will go away. Once this is popped, top will point to this. So once these three are popped, there is only one element left, that is the top element, only one element is left. If you pop that also, what will this code affect? Obviously 10 is obtained. What happens to top? You can see here, top will become q cap next, that is nothing but null. So once you pop this, top becomes null. So immediately you can see that in this particular implementation, the condition for checking, so when do you know that the stack is empty? It's very simple. When the value of top, the pointer, it points to null value. So when top is equal to null, we say that the stack is empty. Otherwise, there are elements in the stack, so you can go ahead and pop. And when the stack is empty, we are not allowed to pop from an empty stack. So that is the behavior of the pop operation on a linked list representation. This is how the push function is implemented. Most of the steps I have already explained to you, even written that. Now it is just put together as a complete function. As you can see, the name of the function is again made as push. It receives one integer value, it does not return anything, and as part of the function, as we have already seen, we need to allocate a new node, which we do it from here using memory, dynamic memory allocation. Then we put the value into the data member of the new node. Then we adjust the link so that the pointer of the newly created node points to the previous top, and then the new top is made to be equal, or the top is now made equal to the newly created element, as we have discussed before. So these 4 lines here, this will create the node, this puts the value into the newly created node, puts the address of the top into the newly created node, and the top is adjusted now so that it points to the newly created node. So with these statements, the push operation successfully takes place. The stack gets modified so that the newly created node will now become the top of the stack. I now want you to look at the complete pop implementation for the linked list, the pop function. As you can see, the name is the same as pop. The return type is int because I am dealing with an integer stack. When you pop an integer stack, we expect to receive an integer value which is at the top of the stack. That's why the return type is int, no arguments. So like before, the pop operation we clearly understand, it simply returns, if the stack is not empty, the value which is at the top of the stack. So we declared one value, integer value, to keep the value of the top of the stack. Node is declared equalized to top, so that q and top both will point to the top of the stack now. We are checking here. What is this check? If top not equal to null, that means this code will get executed only when top is not equal to null. And what is the meaning of top is not equal to null? When top is not equal to null, it means that the stack is not empty, meaning there are elements inside. So this code will get executed only when there are elements in the stack. If the stack is empty, this will be false. So these 2 lines will be executed because it is an error condition. It will simply print stack is empty or empty stack, and the program will be terminated. So this check is to check that, make sure that there are elements in the stack. So when top is not equal to null, these are the 4 statements which you have already seen. Understanding the pop operation, obtain the value, put it into val, q cap data, adjust the links so that top will now point to the next element because the topmost one is now removed. So the next element has to be pointed to by top. This statement does that. This statement will simply deallocate the top of the stack element which we are supposed to remove, and finally this function will return the value because this is the value we are actually interested in the pop operation. And in case the stack is found to be empty, these things won't be executed. It will simply say that sorry, the stack is empty and the program is going to be terminated. So this is the behavior of the pop function. This is an entire implementation of the pop function implementation for the linked list representation of the stack. Stack is the same no matter whether you represent it in one way or the other. The behavior is defined in an abstract manner. The definition of a stack does not talk about the implementation. You can choose to implement it in the way you want, but the behavior has to conform to the definitions of the abstract definition of the stack. So either you use array implementation, or if you use the linked list representation, the behavior of the stack is of course exactly the same. Finally, I want you to look at the isEmptyStack function call. When called, simply this function will tell you whether the stack is empty or not, based on the condition that the top is equal to null or not. Top equal to null indicates that the stack is empty. So the answer will be yes. S in C language is 1. No is 0. So depending on whether the top is equal to null or not, it will either return 1 or 0. So the returned value will be made use of in the place where this function is actually called. For example, in the pop function, we have written if top not equal to null. In place of that, I want you to try and use this function like we have used earlier in the array implementation, rather than directly making the test there itself. So we have seen now the linked representation of the concept or the notion of a stack, which is essentially a last in first out structure. Same operations are implemented irrespective of the implementation, array or linked list. Only the implementation is different, the code will be different. As you have seen in push and pop operations in the linked list representation of the stack, we just need to basically arrange the structure of the links so that the behavior, the desired behavior of a stack is obtained. Thank you.